I'll talk about proportional dynamics in exchange economies, and this is based on joint work with Nikhil, Devanur, and Yuval Rabani. So we study a market model known as an exchange market or economy, where we have a set of n players, and each player I brings an amount xi of goods I. So the good carries the name of the player that brings it, and without loss of generality, we can assume the amount is 1 unit. The utilities of the players are additive. So given a bundle y1 to yn, the utility of player I will be given by some coefficients aij. So it will be the sum of aij times yj, where aij is the value of player I for 1 unit of good j. And we will be interested in outcomes known as market equilibria, where trade takes place efficiently. So these will be given by a tuple of prices p star and allocations x star, so that at these prices, each player sells the goods that they brought, and with the money obtained, purchases a bundle that they like best within what they can afford. The property of the market equilibrium that will be very useful in this work will be that at the market equilibrium, if the utilities are ui star and the prices of the goods are pi star, we have that ui star over pi star is equal to aij over pj star for all edges ij where player I purchases good j in the equilibrium. So there is a lot of work on this problem. There are several polynomial time algorithms for finding a market equilibrium based on convex programming. And one is due to Shahin, which exploits basically cycles in the graph of evaluations, AIJ. And recently there is a result that develops a strongly polynomial time algorithm this is by Garg and Beck. The runtime is like nt11 times log n square. And in this work, we study dynamics, and in particular, we will study a class of dynamics known as proportional response, where the players will exchange throughout time. So basically every day the players will come to the market, they will bring their goods, and what they will adjust will be their investment strategy. So they will repeatedly respond to the current state of the market. And an issue is that in decentralized settings like these, the players may take myopic decisions that look good momentarily, but they will be bad perhaps in the long term. So they may fail to trade efficiently. So there is a lot of work on algorithms and complexity of market equilibria, some of which I include here, and also on tautonomont and various learning dynamics, learning how to bid, and auction dynamics. And there is also work on the type of dynamic that we studied, which is the proportional response. And this has been studied before in Fisher markets and production markets. And there is a dynamic that has been studied in the exchange markets for the special case where the goods have a public value. So each player I has value Vj for each good j. So the valuations are identical. So to formally define our dynamic, I will first explain a high-level description. So each player will start with 1 unit of its good and the budget that it can use to acquire goods. And the mechanism for allocating goods will be trading posts, which is also known as the Shapley-Shubik game, which was proposed by Shapley and Shubik to explain the formation of prices in the exchange market. So in each time unit, the players bring the goods to the market. Each player will bid on the goods, and every good is allocated among its bidders in proportion to the bid amount. And then each player collects the money made from selling and takes the bundle purchased. We look at how the players should adjust their bids. So this is not specified so far. And here they will update their bids proportionally to the contribution of each good in their utility in the last round. So mathematically, this is the dynamical system we study. So each player I starts with 1 unit of good I and the budget bi of 0, which it divides into bids bij of 0. And at each time t, each player I follows the following steps. So it competes for the goods. So it submits bids, bij of t, and it gets from each good j an amount yij of t, which is bij of t. It's bid divided by the sum of bids at good j. And the sum of bids at good j can be interpreted as the price of good j. This is if it bid anything. If it didn't bid anything, it gets 0 from the good. Then the player calculates its utility for the bundle it receives. which is additive, and then it updates its bids for the next round. So BIJFT plus 1. So this will be we have a fraction. So in the denominator, we have UI of t, and the numerator we have aij times yij of t, which represents the utility that player I gets specifically from good j. So this is all this is multiplied by bi of t plus 1, which is the money made from selling in the previous round. So basically, if the player made 1% of its utility yesterday from good j, then it will invest 1% of its money on good j in the following day. So this is an example from a simulation in a 10-player instance over 400 rounds. So it shows the allocations. And you can see that they sort of stabilize in the longer term. This is another instance with 12 players. Here we plot the allocations on the left, the utilities, and on the bottom, the bids, BIJFT. So these have oscillations, some initial oscillations. Initially, they also stabilize in this example. So we show formally that the utilities converge to the market equilibrium utilities for any initial non-degenerate bids. And the way we do that is to look at the KL divergence between the bids at time t and some fixed point bids B star, which are the bids B star represent what the players pay in the equilibrium. And this will give a Lyapunov function, which we show is monotonically decreasing, and it's bounded from below. So basically, to briefly explain what we defined, so we defined some terms Zij of t, which will be Bij star divided by Bij of t and everything to the power Bij star, where Bij star is the spending of player I on good j in the market equilibrium. So this is if the player spends anything on good j. If it doesn't, then the term is defined as 1. Recall we had the property of the market equilibrium that ui star over pi star is equal to aj over pj star for all ij where the spending on player I on good j was non-zero in the equilibrium. And this enables us to R all these terms. So if we look at Zij of t plus 1, then we can write it as a function of Zij of t times some extra term. Then we define a function f of t, which will be the product of Zij of t. And basically expanding f of t plus 1 will give that f of t plus 1 is f of t times some term that depends on the utilities and the prices in the equilibrium. This function, this extra term, is a different function g of t, which has a connection to the Heisenberg-Gale convex program for computing an equilibrium in a related model known as the Fisher market, where we have, it's a bipartite model where we have the buyers and the sellers on different sides of the market. And basically, this allows us to infer that g of t is less than or equal to 1. And moreover, we get that f of t plus 1 is strictly less than f of t at all times t where the utilities are not the equilibrium utilities. The function f is also bounded from below. So we get that the limit exists. And basically that in the limit, the dynamic reaches the market equilibrium utilities. So we also showed that the allocation converges to an equilibrium allocation for any initial non-degenerate bids. And meanwhile, the prices can oscillate. So this is a 2-player example. So here we have a valuation graph. Player 1 has, for example, a value of 38 for good 1 and 79 for good 2. And the initial bids, let's say they're all 1/2. So player 1 starts by bidding 1/2 on good 1 and 1/2 on good 2. And similarly for player 2. So this is a plot with what happens with the allocations, utilities, and prices. And so the allocations and utilities can be seen to converge, which we showed formally. The prices have some small oscillations that go on. This is another valuation graph, which is shown schematically. So this is for 10 players, where the players are divided into 3 groups, C1, C2, and C3. So that the players in group CI only value the goods of the players in group CI plus 1. So here, group C1 contains players 1, 2, and 3, and they only like the goods of players in group C2, which are 4, 5, 6, and 7, and so on. And this is what so we have some numbers on those, but this is what the allocations, utilities, and prices look like. So the prices have quite a lot of oscillations, which we can see on the plot. So we show a combinatorial characterization of cycling of bids. So basically there will be equivalence classes C1 to CK for some integer k less than n, so that in the limit, each two players ij that are in the group, in the same group CL, have price within the same factor lambda L of t away from their market equilibrium price pi star pj star at each time t. We also defined a lazy version of the dynamic where every day each player Y will save a fraction alpha I of its money in the bank and spends the rest for bidding. And everything else is defined the same. So to recap, what that means is that in each round, each player I will submit its bids Bij. The goods will be allocated proportionally to the bids. Then the player collects the money from selling, and then at this point, it takes all its money, whether it has something saved in the bank and some money that it made from selling. And again, it divides it into a fraction alpha I that it saves in the bank, and the rest that it will submit, it will use for bidding. And then the players will update its bids proportionally to the contribution of each good in its utility. This is the previous example that I showed you with 10 players. So here, basically each player spends 100% of its money in each round. And this is the same instance where each player spends 50% of its money in each round. So you can see that this removes the oscillations very efficiently. And we also think it's a natural behavior in some sense. So the players may want to spend some of their money. So the theorem that we show is that the lazy dynamic converges in everything, so in allocation, utilities, and prices, for all saving factors alpha I. So these may be different for different players. So as long as alpha I is in the open interval 0, 1. And this holds for any initial non-degenerate bids. And to show this, we define a weighted KL divergence to explicitly take prices into account. We also bound the rate of convergence of the dynamic with respect to the Eisenberg-Gale objective. This objective is the sum over all players I of BI, which is the budget of the players, times log of UI, which is its utility at a given allocation, which is included in the Eisenberg-Gale convex program. So the rate of convergence that we get is that for each alpha I, the average of the Eisenberg-Gale objective over T rounds converges to the optimum at a rate of 1 over T. So there are some directions for future work. It would be interesting to understand, for example, to show a convergence in last iterate, to study perhaps more general utilities, more general classes of dynamics, and to understand if there are connections with multiplicative weights or gradient descent. Thank you.